look at solving by elimination. It's sometimes called the addition-subtraction method. It's sometimes called linear combination. It has all kinds of different names, but for most people it's their favorite method for solving. It always works when I am solving a system of two linear equations with two unknowns. It sometimes will work if it's a nonlinear system or if it's three unknowns, but not always. And so that's why we need those other methods. So we talked yesterday about if it is just a system of two linear equations with two unknowns, that there are really only three possible outcomes. You can have parallel lines that have no intersection, so you're going to get no solution, because remember we said the key was that solution equaled intersection. You could get intersecting lines that intersect in one place so that you get one solution, and the solution is the intersection. Or you could get overlapping lines that have infinitely many points of intersection, so then they have infinitely many solutions. Those were our three possibilities. So when we solve by elimination, we're going to go through, for instance, in example number 1, we're going to take this system of two linear equations with two unknowns, and we're just going to combine it. We're going to add it like you would if it were a typical addition problem. I'm going to go through and say 3x plus 5x is 8x. 2y and a negative 2y is 0y. 4 and 8 is 12. And so you'll notice my y value just got eliminated. It just dropped out when I combined those two equations. So now I'm left with 8x is equal to 12. And I can just divide both sides by 8, and I've got my solution, right? Nice. A little bit simpler than creating two XY charts and two graphs. All right, so once you know x is 3/2, how do you find y? Plug it back in, right. So I'm going to go through and I'm going to plug in 3/2 in the place of x, and I'll end up with y is equal to negative 1/4. And I'm going to write that answer as an ordered pair, 3/2, negative 1/4. Now, the nice thing about that solution and the solution to any system is you can plug it back in to the first equation. So put the 3/2 in for x and the negative 1/4 in for y, and you'll get 4. Take it and plug it into the second equation. Put the 3/2 in for x and put the negative 1/4 in for y, and you'll get 8. And that gives you a way that you can check and make sure that it really is the solution to that system. All right, so what made that problem so easy? What made it fall together? Why did my y eliminate? Why did it drop out? They had opposite coefficients, right. Their coefficients of the y variable were the exact same number, except for they were opposites of each other, so when you combined them, they canceled each other out, right? So they were kind enough to me in this first example to set it up that way, but when you look at this second example, that doesn't happen. If I were to go through and just add these, I would have 7x minus y is equal to 23. That didn't get me anywhere. And so if they don't set it up for me where a set of my coefficients are opposites of each other, then I can create my coefficients to be opposites of each other. For instance, let's say that I wanted to eliminate x. So I want 5 and 2 to cancel each other out. You can really treat this kind of like you would a least common multiple. Like, what's the least common multiple of 5 and 2? 10. So I could go through and say, okay, if I want this to be 10 and negative 10, then maybe I multiply the top equation by 2 and the bottom equation by 5. I can do that? Yeah, absolutely. Remember, as long as what you do to one side, you do to the other side, it's a legal move. So I can multiply this equation by anything that I choose to, as long as I do the same thing to one side as I do to the other. What if I were trying to eliminate the y variable? What would I want to get? 12, right. So I could go through and multiply this top equation by 4, and I could multiply this bottom equation by 3. And in that case, they're already opposites of each other, right? Whereas if I want this to be 10 and negative 10, I'm going to have to multiply through by like a negative 5 in the bottom. Over here, if I multiply the top equation by 4 and the bottom equation by 3, then I'll end up with 12y and negative 12y, and they'll drop each other out. So you could go either way, doesn't make any difference, but that's what I'm going to do. So let's go through and multiply the top equation by 4. So 4 times 5x is 20x. 4 times 3y is 12y. And 4 times 9 is 36. Most common mistake that I see students make on this type of a problem is we get so obsessed with the left-hand side of the equation and trying to get opposite coefficients and all of that, we forget that what you do to one side, you have to do the other side, and we forget to multiply that 9 by the 4 as well. We forget to multiply that 14 by the 3 as well. So remember, multiply the whole equation, both sides. All right, down here in the bottom, 3 times 2x gave us 6x. 3 times negative 4y gave us negative 12y, and 3 times 14 gave us 42. So now when we go to combine, we eliminate a variable, right? Because we combine 20x and 6x and 36 and 42, our 12y and our negative 12y drop out. And so we've eliminated one of our variables. Okay, so how do we get x by itself? Divide by 26, and we'll get x equals 3. Then how do we find y? Plug x in. So we'll put 3 in the place of x in either one of the equations. I chose the first one. And then we can find y is negative 2. So we're going to write that solution again as an ordered pair, 3, negative 2. Now, a couple of bold print terms that they give us here in the textbook. On the bottom of page 500, the first one they tell me is an equivalent system. These two systems that we were just working with right here are equivalent systems. The original one that we started with, and then the one that we created by multiplying both sides of the equation, the first one by 4 and the second one by 3. Those are equivalent systems. And they tell me in the book that equivalent systems have precisely the same solution set. So if I solved this first system or if I solved this second system, it would be the same thing. The second set of bold print terms that they give me come from page 501, and that's consistent and inconsistent. And they tell me that a system of linear equations is consistent if it has at least one solution. It's inconsistent if it has no solution. So consistent if at least one, so one or more. Inconsistent if it has none. So we've already said these up here at the top, these are our only 3 possibilities for our answers. So if we get parallel lines, is that consistent or inconsistent? Inconsistent, right, because there's no solution there. What if I get one solution, consistent or inconsistent? Consistent. How about infinitely many solutions? Consistent. Good. All right, so let's look at another example. Example 4, we've got x minus 2y equals 3. Negative 2x plus 4y equals 1. I want to eliminate a variable. So, suggestions?
2.
All right, let's multiply that first equation by 2, you say. So if we multiply the top equation by 2, we'll have 2x, negative 4y equals positive 6. And we've created this equivalent system, equivalent to the original that we had. Okay, so we go through and we try to combine 2x and negative 2x. All right, we eliminated our x. 4y and negative 4y. Ooh, hang on, I just eliminated my y too. I didn't mean to do that. 6 and 1 combined to be 7. I got 0 equals 7. What does that mean? No solution. Yes. Remember yesterday we talked about if there's ever a problem that you are working through, whether substitution, elimination, whatever method you're using, if you're solving and then all of a sudden all of your variables drop out and you're left with a false statement, 0 does not equal 7. If you're left with a false statement, that means no solution. That just means that, you can sit here all day long and plug in ordered pairs and you're not going to find one that works in both of these equations. So that's what we're trying to show you here. There's no way that they're equal to each other. Okay? What type of a system would this be? Consistent or inconsistent? Inconsistent. And what kind of lines would these graph has? Parallel lines. On the test, if I give you this system and I say solve this system, what do you put in the handy dandy little answer blank? No solution, right. Don't tell me 0 equals 7. You'll lose points for that because I don't know that you know how to interpret that correctly to be no solution. So be sure you tell me no solution. Don't tell me inconsistent or parallel. Tell me no solution. Now, if right after that it asks you what type of a system is this, consistent or inconsistent, or what type of lines would these be, that's fine. We can answer those questions as they come. But the actual answer for the solution to this system is no solution. All right, let's modify that example just a tiny bit. Let's just change one number. Let's say that this number right here, instead of being 1, let's say that that number was -6. So that when you went through and combined it, everything eliminated. And you ended up with just 0 equals 0. What does that mean?
Parallel.
Yes, it means infinitely many solutions. Exactly. Because what that's saying is I'm getting an identity here. So that's telling me there's not just one thing that will work here. There are multiple things that will work here. So we mentioned that yesterday as well, that if you're solving and all of your variables drop out and you're left with an identity, a true statement, 0 equals 0, 7 equals 7, or maybe all your variables don't drop out and you have like 2x equals 2x or something like that, then that means that you have infinitely many solutions. So would that be consistent or inconsistent? Consistent. And what type of lines would that graph has? Right, overlapping. It'd be one line on top of the other.